This is a joint work with Shahar Dobzinski, and I'm going to tell you today about mechanism design with mole builders. Many of the works in algorithmic mechanism design look for truthful mechanisms. These are mechanisms in which we incentivize the bidders to report their true valuations. The underlying assumption here is that if we don't incentivize the bidders to report their true valuations, then whenever they can profit from lying, they are going to lie. But is it really the case? Research from behavioral economics suggests that it's not necessarily the situation. In a very cool experiment, Fischerbacher and Folmy asked participants to roll a six-sided dice in a cup and report the results. The payoff of the participants was determined as a function of the number that they reported. So the higher the number, the higher the payoff. Now, only the participants saw the number that they rolled, so in principle, they could always report 6 and collect the maximum payoff. What's nice about this experiment is that even though we cannot tell if a certain individual lied or not, on the aggregate, we can tell how much the distribution of reported values is different than the distributions of values we expect to get from a fair die. This experiment was run many times, different populations, different variation, and in 2019, Abel et al. Published a meta-analysis, including 90 papers. And they reached the following conclusion. Participants only collect about 25% of the potential gains from lying, so they don't say 6 all the time. The following graph is taken from a website accompanying this meta-analysis, and this includes all data from experiments that were run in Israel. So different colors correspond to different experiments. On the x-axis, we have the value reported. On the y-axis, the percentage of people reporting it. And the dashed line is the line of 1/6, so what we expect to see if people report truthfully. And it's pretty clear here that 1 and 2 are underreported, while 4, 5, and 6 are overreported. And especially 5 is overreported, so people do not lie to the full extent. A couple of explanations that could explain this phenomena are first that there is some cognitive cost for lying, and second, this idea of social identity. So this means that we care about our perception by others, even strangers, and by our own self-perception. And to keep our social identity in line with our moral standards, then we will try to refrain from lying as much as possible. Another experiment about lying, which is more related to the setting we are interested in, was run by Gneezy in 2005. In this experiment, there are two participants. One plays the role of the sender, and the other plays the role of the receiver. Now, the receiver needs to choose one of two alternatives, either A or B, and only the sender knows the payoff for each alternative. So, for example here, for alternative A, the sender will get 5, and the receiver will get 6, and for alternative B, sender will get 6, and receiver will get 5. Now, based on this information, the sender chooses which message to send. So she can either choose to send a message, option B will earn you more money than option A, or the opposite message. And now the receiver makes its choice, and the payoff is realized according to the chosen alternative. Now, 80% of the senders actually believe that the recommendations will be followed. In all treatments, the option that gives more money to the receiver is option A. So when the sender recommends option A, this is telling the truth, and when the sender recommends option B, this is lying. In this experiment, they did 3 treatments. So here are the payoffs for the different alternatives in the 3 treatments. In the first alternative, which is the one we just considered, then 36% of the senders lied, so they recommended option B. And this is a fairly symmetric treatment in which there's not too much to gain by lying. The second treatment, only 17% lied. So now, again, the sender has relatively has not so much to gain by lying, but the receiver can lose a lot. So just 17% lied. And in the last alternative, when there is a lot to gain from lying, 52% lied. And what we conclude from this, that when the benefit from lying is smaller than the receiver's loss, then senders tend to lie less. From the experiments we presented and other related experiments, we can conclude 2 behavioral assumptions. First of all, individuals have a preference for truth-telling. We can see this in the first experiment, where people do not lie to the full possible extent. Second, individuals care about the damages to others. So in the second experiment, when the damage to others was high, people refrain much more from lying. In this paper, we refer to people obeying these two assumptions as moral bidders and define mechanisms in which they will report their true valuations. The rationale here is that a player will only lie if his profit from lying is larger than alpha times the sum of losses of the other players. And alpha here is a parameter between 0 and 1, capturing the extent of, say, morality of the bidder. Let me tell you about our mechanism a bit more formally. So the setting we consider is a single item. There's one item that we need to allocate to one of the players, or we could choose not to allocate it at all. We consider deterministic mechanisms that are both individually rational, so the payoff of the bidders has to be non-negative, and no positive transfers. The mechanisms cannot pay the bidders. Now, formally, a mechanism is a pair of f and allocation function gets the player's value for the items and returns the identity of the player that the item will be allocated, or it can choose not to allocate the item at all, and a payment function returns each player the payment that it should pay. So a mechanism is alpha moral if in every instance v1 through v1, vn, v1 through vn, for every player I and vi, such that player I can increase his profit by lying, so reporting a default value v prime I, his profit from lying has to be at most alpha times the sum of losses of the others from the lie. So let me walk you through the notation here. This is the profit of player I, that its true value is vi for reporting a different value, v prime I. So this difference is the profit from lying, and we want this to be less than alpha times the losses of the other players. A couple of things to note about our mechanisms. So first, a truthful mechanism is zero moral. So if we put 0 here, this would mean that the profit from any lie has to be less than or equal to 0. So the player cannot profit from lying. Second, the assumption for preference for truth-telling appears here in that the bidders measure gains and losses with respect to truth-telling, which is considered the default options here. It is important to note that our bidders are not altruistic. They do care about maximizing their own payoff. Only when the bidders need to decide whether to lie or not in order to increase their payoff, they compare the benefit from lying versus the damages that they will inflict upon others. This behavioral assumption fits better situations in which the bidders know each other. Think, for example, about an academic department that need to decide who will get some expensive piece of equipment, so for example a microscope. Then probably people will have harder time lying and saying that they have a high value for this equipment when they know that other people need them more than they do. I want to demonstrate how moral mechanisms work using two examples. First, we will see that moral mechanisms can be used to implement the same allocation function as truthful mechanisms, but with different payment functions. So here we consider the natural mechanism that allocates the item to the player with the highest value. And a truthful mechanism can only implement this allocation function by charging the highest value bidder the critical price, which is the second highest value. Moral mechanisms, on the other hand, have much more flexibility, and we can see that a moral mechanism can, for example, charge the highest value player half of the second highest value. So we will show that this mechanism is one moral. So let me just remind you what we need to show for one moral mechanism. We need to show that the profit of each player for lying, if this is positive, is at most the sum of losses of the other players from the lie. Okay, so let's use Vk to denote the value of the player with the maximal value, and Vj denote the value of the player with the second highest value. It is easy to see that player K cannot lie to increase its profit, since the value that it reports doesn't affect his profit, and he is already winning. A player that can affect his profit is some player I that may be able to increase his profit by reporting Vk plus epsilon. By doing so, this player will become the highest value player. Okay, now let's see if in a moral mechanism, a player I could do this. So what we require is that the profit of player I from this lie, which is this, okay, so if player I would report VK plus 1, you will get the item for a value of VI, and the second highest value will be VK, so this would be his payment. And we require this to be less than equal than the profit that player K had for getting the item, which is VK minus VJ over 2. And this inequality indeed holds since VK is the highest value. Yeah, so this mechanism is one moral mechanism. The second example we will see demonstrates that moral mechanisms can implement allocation functions that cannot be implemented by truthful mechanisms. In particular, we observe that the allocation function of a moral mechanism doesn't have to be monotone. Recall that the monotone allocation function is one in which if player I won the item when reporting VI, he will also win it by reporting any value greater than VI. And a famous characterization tells us that when we allocate a single item, then we can only implement monotone allocation functions by a truthful mechanism. Okay, so what we will see now is a non-monotone allocation function that can be implemented by a one-moral mechanism. So the allocation function is given by the following picture. So here this is the value of player 1, and these are the values of player 2. The green area, the gray areas are areas in which we don't allocate the item at all. So when V2 is less than 1/10 and V1 is less than 1, we don't allocate the item at all. Blue area, we allocate the item to player 1. And in this case, we charge player 1 1. And red, we allocate the item to player 2 and charge him 0. So we allocate the item to player 2 only in the case that V1 equals 11/10. Now this is obviously, this allocation function is obviously non-monotone, since if we are here, and player 1 increases his value to 11/10, then suddenly he doesn't get the item anymore. Okay, so let's see how we can, why this mechanism is one moral. First of all, if we are in the gray area or blue area, then it's relatively easy to see that player 1 cannot gain anything by lying. So if we are in the blue area, then player 1 is already getting the item and his price is 1, so misreporting its value wouldn't change that. If we are in the gray area, then player 1 here could misreport his value for something greater than 1, but then since the payment is 1, his payoff would be negative. The more interesting part is here when player 2 is allocated, so V1 equals 11/10. We distinguish between two cases. So either V2 is less than 1/10, so we are here, and in this case, player 1 doesn't want to misreport its value, since by doing so, it will only get the item to be not allocated to anyone at all, so it doesn't gain anything from that. If we are in this area, then it is slightly more complicated. And now we need to compare the profits of player 1 from misreporting, so from getting to this region, versus the loss of player 2. So if player 1 will misreport its value, his profit will be 1/10. Okay, so his value for the item will be 11/10, and the payment is 1, so this is his profit. This was his profit for telling the truth, and we require this to be less than V2 minus 0. Now, since we are in the region where V2 is greater than 1/10, then this inequality indeed holds, and a player that is one moral wouldn't misreport his value in this case. So the mechanism we just presented, in which the allocation function is non-monotone, is a one moral mechanism. The examples we've just seen demonstrates that moral mechanisms extend both the set of embedded allocation and the payment functions supporting them. So main question is whether an auctioneer that only cares about maximizing its own revenue can take advantage of the morality of the bidders in order to increase its revenue. And the answer is that it depends. Let's first see if the auctioneer can increase his revenue by using a different payment function for an allocation function that is also implementable by a truthful mechanism. The following proposition tells us that it's not the case. So consider a truthful mechanism M and an alpha moral mechanism M prime, both implementing the same function f. Then we claim that P prime, the price for the alpha moral mechanism, is at most P, the payment for the truthful mechanism. And let me give you the gist of the proof. So first of all, we observe that every alpha moral mechanism is payment independent. This means that the price of the winning player doesn't depend on its value. Now, let's assume towards contradiction that the price that player I pays in the alpha moral mechanism is greater than the price it pays in the truthful mechanism. Okay, this is the price that player I pays when he wins. Now, in the truthful mechanism, we know that the price that the player pays is its critical value. And in the truthful mechanism, we also know that we can only implement monotone functions. So this means that player I would win the item in all of these regions. Now, since both mechanisms implement the same function, this means that if player I's value is someplace here, then in the alpha moral mechanism, he will win the item, but it's going to pay something much greater than his value. So his payoff would be negative, in contradiction to the fact that the mechanism should be individually rational. So we conclude that the auctioneer cannot increase its revenue by implementing a function that also implementable by a truthful mechanism. This implies that the only possible benefit of moral mechanisms in terms of revenue is when implementing new allocation functions. Recall that when considering the question of revenue maximization, we assume that the values of the bidders are drawn from distributions that are known to the auctioneer. Our results demonstrate that when the player's values are drawn IAD, the auctioneer cannot exploit the bidder's morality. However, when the valuations are drawn from a quality distribution, there are cases in which the auctioneer can exploit the morality of the bidders to increase its revenue. More formally, for independent valuations, we show that when the player's valuations are drawn IAD from a standard distribution F, I will tell you what we mean by standard in the next slide, then for any alpha moral mechanism M, there exists a truthful mechanism M prime that extracts at least as much revenue. For quality distributions, we observe that there exists a two-player quality distribution for which an alpha moral mechanism can extract a higher revenue than any truthful mechanism. Our proof that when the bidder's valuations are drawn IAD, the revenue of a moral mechanism cannot be higher than the revenue of a truthful mechanism holds when the distributions are standard. Standard distributions include uniform distributions and exponential distributions. Formally, these are distributions such that for every value Vj greater than Vi in the support, we have that Fvj is at least Fvi over 1 plus Fvi. Now, a natural approach for proving such a theorem would be building on Meyerson characterization of optimal auctions. Meyerson characterized the payment function in terms of the allocation function. Given the characterization, Meyerson proof completely ignores the payment function and continues to find the allocation function that maximizes the revenue. This approach inherently fails for moral mechanisms, since we observe that the allocation function of one moral mechanism is almost unconstrained. Thus, we need to develop all the machinery required for proving the theorem from scratch, which makes our proof quite complex. Our proof techniques provide an alternative proof to Meyerson characterization of optimal auctions when the values are drawn from independent regular distributions. So we show that the mechanism has to be second price auction with virtual valuations and reserve price. Let me summarize. Our work joins the growing literature in algorithmic game theory, incorporating behavioral assumptions into a well-studied setting. Here we develop and analyze mechanisms for moral bidders. Our main result is a constructive proof showing that for standard distributions and values drawn IAD, moral mechanisms cannot extract more revenue than truthful ones. What's nice about our proof is that as a byproduct, we obtain an alternative proof for Meyerson characterization, one that gradually exposes the mechanism. For correlated distributions, we show that moral mechanisms sometimes do extract more revenue and may extract up to twice the revenue of truthful ones. Let me mention some open questions. So first of all, it will be great to try to apply our techniques to get a characterization of truthful mechanisms beyond regular distributions. Also, here we focused on the setting of selling a single item. Can we apply moral mechanisms to more general settings like combinatorial auctions? And more generally, I think that studying other relaxation to truthfulness, for example, as a way to circumvent some of the impossibility results in the field, could be quite fruitful endeavor.